This video is going to look at kinetic energy and specifically how energy relates to motion. So kinetic energy is the energy associated with the motion of an object. So if an object is moving, the energy associated with that motion we call kinetic energy. And it's got a bunch of properties. Let's go through kind of describing those ideas. So the quantity kinetic energy is a scalar. You either have a certain amount of kinetic energy, it doesn't have a direction, that doesn't make sense. The variable is typically written as Ke. The units are like all energy, joules, which will be written with a capital J, and 1 joule is equal to 1 kilogram meters squared per second squared, which is also equal to 1 Newton meter. So all three of these are equivalent. But when we're talking about energy, we're typically talking about joules. So this is where I said earlier, when we're talking about work, we talk about Newton meters. When we talk about energy, we talk about joules. But because they're equal, we can get away with saying one in place of the other when needed. So now, the equation that we use for kinetic energy is that a change in kinetic energy is equal to 1/2 the mass times a change in velocity squared. So now, this is our equation because as we talked about as we'll talk about throughout this unit, you can't calculate the absolute amount of energy. It's not possible. We don't have any devices that directly measure energy. All we can measure or calculate are changes in energy. So that's why you see the change in kinetic energy is equal to 1/2 m times the change in the velocity squared. Now, connecting this back to the energy interaction model, in this case, the constant is 1/2 the mass. And the indicator is speed squared. So if you get the speed of an object and you square it, and that value changes, then the kinetic energy changes. And so you'll notice, for example, if you change your velocity from 50 meters, it doesn't matter which direction you're traveling, you can change your velocity without changing your kinetic energy, because you can go from positive 50 meters per second to negative 50 meters per second. But your speed squared in both of those cases stays the same. Therefore, there's no change in that energy system. The constant is the 1/2 m. So let's look at a couple examples, and those will also help us, process and think about it. So first, how much kinetic energy is gained by a 60-kilogram sprinter increasing their speed from 3 meters per second to 4 meters per second, and then also from 4 meters per second to 5 meters per second. So in part A, we have delta Ke is equal to 1/2 m times delta v squared, which is equal to 1/2 of 60 kilograms times delta v squared. So that means it's going to be, we erase that, sorry, v squared, so final squared is 4 meters per second squared minus initial squared of 3 meters per second squared. And that will give us 1/2 of 60, so 30 kilograms times 16 meters squared per second squared minus 9 meters squared per second squared. So the first change in kinetic energy is equal to 30 times 7. So I believe that's 210 210 kilograms meters squared per second squared, or in other words, 210 joules. And for part B, delta KE is going to equal 1/2 of 60 kilograms times 5 meters per second squared minus 4 meters per second squared, which is equal to 30 kilograms times 25 meters squared per second squared minus 16 meters squared per second squared. So in other words, that's a delta KE of 30 times 25 minus 16 is 9, so 30 times 9 is 270 joules. So note, we must square the speeds before we subtract them. If we subtracted then squared, we get a difference in speed of 1 in both cases. And we'd get, therefore, in both cases, just 30 joules as our change in kinetic energy. In other words, every 1 meter per second of speed increase would equal a fixed amount of increase in energy. And that's not what happens. The energy increases exponentially as you increase the speed. And that's because it's a change in the speed squared, not change in speed quantity squared. As a second example, how much kinetic energy is gained by a car of 1,000 kilograms when it goes from rest to a speed of 15 meters per second? So delta KE is equal to 1/2 the mass of 1,000 kilograms times 15 meters per second squared minus 0 meters per second squared. So that'll be 500 kilograms times 225 meters squared per second squared. You can do that calculation out, plug it into a calculator, figure it out. But the reason I wanted to highlight this is that, as a reminder, we can only technically calculate changes in speed. But there might be places where you see it given just that kinetic energy, so you might see something like KE equals 50 joules. What is implied there is this is how much more than when the speed is equal to 0. So in order to calculate energies, we always have to calculate changes, but there's some natural reference points that make sense. For example, speed of 0, that if we compare to, we can kind of say this absolute value of the kinetic energy is some number. So that's, I don't like it, but that is how the AP test, I believe on the equation sheet, has it. They say the kinetic energy is 1/2 mv squared. Technically, that's saying this is how much kinetic energy it has more than when that object is at rest. So you can use that, it's fine, just recognize that you're not technically calculating kinetic energy, you're calculating everything relative to the object being at rest.